AP Cram, Calculus AP, Free Response Exam Review. Question 7, Rate of Change, the first derivative. All right, so let f and g be the functions defined by f of x is equivalent to 1 plus x plus e raised to the x squared minus 2x power, and g of x is equivalent to x to the fourth minus 6.5 x squared plus 6.6x plus 2. All right, so this function or this curve right here is g of x, and this one is f of x. Let R and S be the two regions enclosed by the graphs of f and g shown in the figure. So planar region R and planar region S. Let H be the vertical distance between the graphs of f and g. Right, so this can be considered H, the distance between in region S. So specifically, we're concerned with region S. Find the rate at which H changes with respect to x when x is equivalent to 1.8. All right, so just to let you know, this point right here on the x-axis is 1.302 approximately. It was computed earlier in flashcard set 5 of this series. So now you're concerned with 1.8, okay? So if this is 2, 1.8 is somewhere around this region. I'll give you a moment to think about your strategy. All right, so what one has to realize is that the rate at which h changes is code language for the derivative of h. Okay, a rate of change is just simply a derivative. And if h is defined as the length in region S, that means it's bound by f on the top and g in the bottom. So you basically just have to find the derivative of the difference between functions f of x and g of x. Okay? All right, so that's basically what you have to do. And solving the derivative for function f is not straightforward. Whereas solving it for g is straightforward. You just simply take the derivative term by term. But this term right here complicates things a little bit much. And I recommend just putting it in your calculator. Part 2 or the free response section of the AB calculus exam is just really an exercise in using your calculator correctly. But for those of you who are, a little erudite, brainiacs, and you want to know the precise way to go about solving this derivative here, let's just take a quick detour. All right, so I've written out the derivation expression a little differently. 1, I shifted the x to the back, and plus 1 plus x plus e to the negative 2x plus x squared, okay? Now what we're going to do is distribute the derivation function and differentiate each sum term by term. So you have the derivative with respect to x. Okay, recall we're deriving with respect to the variable x. Of 1, the derivative plus the derivative with respect to x of e to the negative 2x plus x squared, and plus the derivative with respect to x of x, all right? So when we evaluate our first term, the derivative with respect to x or y or whatever of any constant is just going to be 0. I'm sure most of you know that. If you don't know it, now you know. There's no variable here to differentiate, so the constant just transforms into a 0, okay? So now we can get rid of this. All right. So now we're taking the derivative with respect to x of e to the negative 2x plus x squared plus the derivative with respect to x of x. Again, we can simplify this expression because it's pretty straightforward. If we pretend that this is x raised to the first power, the derivative with respect to x of x just becomes 1, okay? And now what about this term? It's like a function within a function. So what we're going to do is use the chain rule. And something that I kind of sort of like to call use substitution, although it's not necessarily. So you have the derivative with respect to x of e raised to the x squared minus 2x power, okay? So we're just going to let this complicated term in the exponent portion of the expression be equivalent to u. So now we're taking the derivative with respect to u of e to the u times the derivative. And okay, whenever we have a complicated function, we analyze the outer function, which is going to be e to the u, and then we analyze the derivative of the inner function, which is x squared minus 2x. So the derivative with respect to u of the inner function, which is x squared minus 2x, is equivalent to 0. That's where this 0 comes from. Okay, because first you analyze the outer times the inner function. That's what the chain rule says, okay? And you're going to take the du of x squared minus 2x. So there are no u terms here. So that's why this just turns into a 0. Okay? And then we know the derivative, we're going to see that the derivative of e to the u with respect to du is going to just give us e to the u. All right, so we already established that u is equivalent to x squared minus 2x. Therefore, du of e to the u is equivalent to eu. This is just a rule you have to remember. The derivative with respect to the variable of e raised to that variable is just going to be the same expression, e raised to that variable, okay? So now we can go ahead and plug this thing in, and remember that in the chain rule, first we take the derivative with respect to the outer function, then we have to take the derivative with respect to the inner function and the variable that's contained in that inner function, okay? So don't be confused. There's like, I don't know, 3 things going on in this one expression right here, but that it is what it is, okay? So this whole thing right here came out of this. All right, so we have our e to the u, or e to the x squared minus 2x times the derivative with respect to x, because we still can't leave this term out. We have to take the derivative with respect to x of the inner function also, of negative 2x plus x squared. You can hardly see it now because I scribble all over it. And we still have our d dx of x, which I said is going to be 1 earlier. So we're going to differentiate the sum term by term and then factor out constants. All right, so let's just analyze the more complicated thing. We factored out the e to the negative 2x plus x squared. Now we're going to differentiate. All right, so this is what we left off on the previous card
with respect to x.
So
and
now
negative
we're
2x
going to
with
analyze
respect to
that
x.
the derivative
Well,
of
we
x
can already
is
just
1.
factor out our 2. That's where this comes from.
All right, so first we're going to analyze it within this expression. d dx of x is 1, so this becomes a 2 times 1, okay? And also, we can bind the 2 and the 1 to get negative 2. We can also analyze that this expression d dx of x is 1 as well, okay? Now, in order to analyze this, we can use the power rule that says that d dx of x to the n equals n times x to the n minus 1. When most people think of differentiation, what they usually are thinking of is the basic power rule. And in this case, n equals 2, because see here, this is x squared. So d dx of x squared is going to give us 2 times x to the 2 minus 1, or 2 times x to the first power, or just simply 2 times x, okay? All right, so now we can go back in here and replace this derivative with a 2x. And so our answer comes out to be 1, the 1 was taken from here, plus e to the negative 2x plus x squared times negative 2 plus 2x. Okay, this is just like the long drawn out version to show you precisely where this comes from. All right. All right, so now that we've taken that long detour, let's get back to the original question, and that's analyzing the rate of change of h at 1.8. X is equivalent to 1.8, which is approximately somewhere over here. So we already established that h would have to be f of x minus g of x for the region S, okay, because that's the region that we're concerned with. And in order to establish the rate at which h is changing, that's basically code language for taking the derivative. So the derivative of h prime of x is the same thing as saying the derivative of f prime of x or g prime of x. This is just derivative notation, so if you're not familiar with it, I don't know, Google it, okay? And so in our long detour, we found the derivative of g prime of x. And if you want to know we found the derivative f prime of x, and g prime of x is pretty simple because you just use the power rule. So the derivative of g prime of x would be 4x to the third times, what is this? This would become negative 13x. This would become 6, and the 2 would be lost. It would be 0 because if you're taking the derivative of 2 with respect to x, there's no variable, so the constant becomes 0, okay? So if you plug in 1.8 into f prime of x minus g prime of x, the answer, or the rate of change that you're going to get, is negative 3.812, or some of you might get negative 3.811, depending on which calculator you're using. And remember, use your calculator to take these derivatives. This is not the time to show your skill in differentiation on the AP exam. If you have an in-class exam and your teacher requires you to express the derivative term by term, then you might have to, but not for the AP, okay? The AP is a time task that not only wants to see your knowledge, but they want to see how you handle such problems under constricted or restricted amounts of allowed time, okay? So our rate of change is negative, and this makes sense because as you traverse from left to right in region S, you see that
the gap is kind of closing between f of x and g of x. So it makes sense that h is being reduced, or the derivative is negative, okay? It doesn't mean that this has to be found in a negative quadrant. It just means that the rate of change is becoming smaller, okay?